Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 1 of 4 on the topic of simple linear regression and will cover an introduction to linear regression. Let's get started. In the next 4 videos, we will build on concepts in exploratory data analysis and multivariate analysis to develop simple linear regression models and later multiple linear regression models. But first, we should discuss exactly what linear regression is and why we use it. Regression is used when we have data that we observe about 2 or more variables jointly, and we want to make inferences about one variable assuming it's dependent on another. It lets us assess the strength of relation between 2 variables. It also gives us a formal way to talk about our confidence in predictions about the dependent or response variable. Usually with regression, we're interested in the line of best fit, that is, finding the line that passes through the data and has the smallest possible error. We measure the error along the y-axis, that is, only in terms of variable b, which is the one that we're trying to explain. The line has 2 parameters, a slope and an intercept. When we first encountered the equations for lines in geometry, we usually see it as y equals mx plus b. But in statistics, we replace the intercept with beta naught and the slope term with beta 1, so that if we want to add extra predictors to the model, we don't have to start picking new letters for that coefficient, it just becomes beta 2. In this situation, we search for the values of beta naught and beta 1 that minimize the distance between the line and the points. For any straight line you draw, or for any value of beta naught and beta 1, unless your data make a perfect line, there will be some error left over. At each point, you can apply the regression model by plugging in the observed x value and getting a predicted y value. The predicted value is labeled as y with a circumflex accent. Usually we just shortcut this by calling it y hat. The circumflex accent is usually used for estimators, as in the estimated value of y. You can take the difference between the observed y value and the predicted y value to get the error of the prediction at that point. In regression, we call this error the residual, here labeled r. Truth be told, the residuals are what regression is all about. For any individual point, to get from the predicted value y hat to the actual value y, we must add in the residual for that point. Now say you have a model and you want to predict the value of the response variable y given a value of x. For example, say you've constructed a model that predicts annual stream flow volume for a watershed using annual total precipitation as a predictor. You then want to predict the annual stream flow volume for a hypothetical value of annual total precipitation of, say, 40 inches. You don't know the residual value in this case because the stream flow volume for your hypothetical rainfall has not yet been observed. You can only talk about the predicted value in terms of probability. The outcome is random and therefore uncertain. On the left is a best fit line through some data points in blue. This line has a slope and an intercept that minimize the total error between the points in the line in the y direction. When you take all the residuals, which are the leftover errors from the regression, and you plot them as a density, you get the result on the right. The density is a way to show the probability distribution empirically. Each tick along the x-axis is one residual value. The density gives a relative sense of how frequent those residual values are, with a higher density value meaning those values come up more often. You should see a couple of things in the density on the right. 1. Most of those residual values are clustered close to 0. That means for most points, the residual error is small. 2. You should see that the errors are about even in both directions away from 0. That is, there are positive and negative errors of about the same magnitude. Third, there are only a small number of very large residuals. The shape of the empirical density on the right helps us see what the distribution of these errors looks like, and as the sample gets larger, this will look more and more like a normal distribution. Because the regression line isn't a perfect fit, the regression equation does not explain all the variability in the y values. This leftover amount of variability is a random error centered at 0. This means that a prediction of a y value corresponding to any desired x value depends on the regression line, but also the error term added on the end. The true y value is unknowable for the given x value. Using the regression equation provides the mean estimate for the predicted y value, but the real value can only be described in terms of a prediction interval, which is an interval with a width defined by the residual variance. The plot on the right shows a regression line with the 95% prediction intervals around it. The red line is at about x equals 52. The mean estimate of the y value corresponding to this x value is about 100. However, due to the random error of this model, there is a 95% probability that the true unobserved value of y is between 70 and 130. Creating the prediction interval we just saw involves taking the distribution of the residuals and sliding it along the regression line. The 95% prediction interval contains the yet unobserved y value 95% of the time, and it's a symmetrical interval, so 2.5% of the values fall above and 2.5% below this interval. This means, while sliding the residual distribution along the regression line, we mark off the 2.5% and 97.5% percentiles of the distribution while moving it along. This assumes that we know the true values of beta naught and beta 1, while in reality there's uncertainty in those values. We will see later how to compute intervals that account for this uncertainty. Remember that the regression line is the conditional mean value of y given some value of x. The true value is unknowable, and we could talk about it only in terms of a probability distribution. It is important then to determine what the distribution of the residuals is in order to be able to do things like create a prediction interval, or to get a sense of how reliable our estimates are using this model. For simple linear regression, we assume that the residual is normally distributed. As a result, the response variable y is also normally distributed. On the plot, you can see that for each value of x, the corresponding output is not a single value, but a conditional normal distribution with a mean determined by the regression equation and a variance computed from the variance of the residuals of the model fit. This means we are fitting the conditional distribution of y given x. This implies that there's some joint distribution of x and y, as we saw in multivariate analysis. This is one of the major assumptions made when performing linear regression. In the situations where we find that we violated this assumption, there are options for fixing it, which we'll discuss in Part 3. However, there are 3 other assumptions also being made when using linear regression. There are 4 assumptions being made when using a linear regression model. These assumptions represent several trade-offs. On one hand, it seems restrictive and narrow with some specific assumptions. On the other hand, when we meet these assumptions, the model is easy to fit and to use to make inferences. The first assumption states that the relationship between the variables is linear and not something else like polynomial. The second assumption states that the variance is constant and that the residuals from the model fit have the same spread across the range of fitted values. The third assumption states that the values of the residuals have a normal distribution or are reasonably like a normal distribution. The fourth and final assumption states that each error is independent of the others and does not exhibit serial correlation. We will go over checking these assumptions in Part 3. In this video, we covered an introduction to simple linear regression. 2 key points to take away from this video are: regression is a tool that helps us evaluate the dependency of a response variable on some independent predictor variable, and there are 4 important assumptions to keep in mind when building a linear model. Thanks, and tune into the next video in this series on simple linear regression to learn about constructing a simple linear regression model.